So now let's start analyzing this motion that we're going to have. Of course, this is done in high school as well. So if this is v0, right, the initial velocity, and the angle here, let's call this phi, then this is going to be the component of velocity. This is v0 cosine phi, and this is v0 sine of phi, and we'll assume that the origin here is 0, 0. That's the origin of our coordinate system. This is y, this is x. And of course, the acceleration here is taken to be minus g. This is basically just a convention. If we choose the y-axis to be pointing upwards from the Earth, right, not towards the center of the Earth, and g is pointing towards the center of the Earth, then of course g is going to have negative value here of negative 9.8 meters per second squared. Okay, so here, of course, if we want along this trajectory to parameterize and know each, suppose that we have a ball here, or something that is moving along this trajectory, and we want to know its position at every time, x of t and y of t, then of course for x it's just as simple as it gets, because in x we don't have any force that is interfering, so we're going to have v0 cosine of this angle phi that I chose, n times t. Basically it is as simple as saying that distance is a velocity times time, right? Velocity times time is the distance here, because there's no force interfering here. And along the y-axis here, we're having the force of gravity that is acting here. And of course, it's a motion with constant acceleration, this acceleration. And so for y of t, what we have is that we have 0 sine of this angle phi and minus half gt squared. Right. This is, of course, times the t, times t, and yeah, and minus that. And so if we have an origin in another place, right, so this is our origin and we want to describe a motion from other point, then basically we would just add x0 and y0 to this x here. But this is not of real interest to us in this problem, but the general equation would be x of t is x0 plus v0 cosine of phi times t, and y of t would be that's just y0 and plus this v0 sine of phi times t, and minus half g t squared. So that would be the equation of motion for an arbitrary point, and then from this point, if the particle was shot, then we would make all the computations. So what would we be interested here in the geometry of the problem is, of course, to show that this is a parabola. And so what we want to do first is to define this range and maybe to find this peak. So we will call this point here the distance of in the x direction as a function of the angle phi, d of phi, and this is going to be the x of phi, and this is going to be just dy of phi, right? And from symmetry here, it can be actually proved that this is in the middle, so it's the x divided by 2. Okay, so for this, what we need to derive here, of course, is that when y equals to 0, right, when it hits the ground. So again, I'll write here y of t is this v0 sine of phi times t, and minus half gt squared here. And so in order for this to be equal to 0, right, we want this to be equal to 0. Those are 2 points. So for t equals 0, of course, this is 0. And then if t is not 0, we can divide by it. And so we get that this time of flight for the particle here is that this is going to be, we move it to the other side, and then this is basically going to be twice v0 divided by g, and this is sine of phi, right? If we move it there and then divide. So this is our time of flight. And at the middle of our time of flight by symmetry considerations, then we're going to have this peak. Okay, so now if we want to figure out the range here, so as a function of this angle phi, so what we need to do is to take this equation for x and substitute this t. So dx, this dx as the function of the angle phi, is going to be v0 cosine theta, cosine phi, times this times 2v0 over g, and sine of phi. And then using this trigonometric identity, what we get is this is v0 squared divided by g sine of 2 phi. And what we see here, of course, is that this is maximum when sine is 1, that is phi equals pi quarter of radians, of course, 45-degree angle. And we'll see this in the visualization, because when the angle is high, then it has a lot of time of being in the air, but then the velocity component in this direction is small, so it is a lot in the air, but it doesn't really move forward. And when we throw it most of the velocity here, then it moves fast here, but then doesn't have enough time in the air, so it hits the ground. Okay, so now let's try to visualize and code this into Desmos, and hopefully you'll learn something about how Desmos works here. Okay, so let's write this, and when you're writing in Desmos simulation or visualization, try to think of it in patterns of like software development. So we'll give this a name. So call this f of t, and then t in parametric plot is something that is reserved. It's this dummy variable. So we'll write v0, right, times the cosine of, and I'll call here phi. I write phi, and then Desmos understands that this is the Greek letter phi, and so this is going to be times t. This is the x component, of course, and here we're going to have v0, and look how easy it is, times the sine of phi, and times t here, of course, and minus 1/2 times g times t squared. Sorry, wanted to write it here, times g times t squared. And notice how nicely it writes this in LaTeX style, in this formula, in equation style, all of those. And now Desmos understands that this t is a reserved value for for plotting. This is dummy variable, and those are undefined. And so he suggests to add sliders to all of them, so or to any of them. So let's add them. And so for the velocity, let's set it to be in the range of 0 to, I don't know, 20 meters per second is quite a lot. All right, it's rough. It is 72 kilometers per hour, right? So it's let's give it a step of 0.01, and let's give it a step of 0.1. And the angle phi, will let it be from 0 to pi, actually 180 degrees, and we'll give it a step of 0.01. And here, of course, g will set it from 0, maybe 0 gravity, up to some gravity, say here 10, so that we can simulate the effects of gravity, and we'll give it a step of 0.1, and here we have 9.8, right? Set it to 9.8. This is g. Okay, and so we have set this g here, and this is f of t, right? And let's move it over here, and basically we want the sliders that are going to control the simulation upwards, and all the definitions here. So we've defined this function, but we didn't say to plot it. And so now let's add a constant. We would want to have the constants beneath. So this constant time of flight, we have computed that this to be 2v0 divided by g, and this is times the sine of phi, all right? And now we can use all those values for this to update and adjust in real time. So now I want to plot f of t, and it will ask for me for the range, and it will be between 0, of course, and the time of flight. So this is t, and so we can now zoom in and see this trajectory for the angle, and here we can actually see how the trajectory changes with the angle. So for example, and with the velocity. So if I increase the velocity here, then we see that it is changing. I can see the effect of gravity. So for smaller gravity, it will fly higher, of course. For smaller gravity and a higher gravity, it will fall faster, of course. So let's put it back to 9.8. And of course, the dependence of the trajectory on the angle. So we see that for angles that are close to 90 degrees, it gets a lot of air time, yeah, and gets higher, but then doesn't have enough velocity component to move forward, mostly in the air. And for shallow angles, starting from some angle over here, it doesn't get enough time in the air, it crushes the ground. And so 45 degrees, just taking the middle, is taking the best of the two qualities here. So if I'll set phi here to be pi quarter here, this is the maximum range here. Okay, what else can we do here? We can actually define a point here. Let's call this f of c here, and let's add a slider for c, and let's c be from 0 to capital T, and again let's make it a step of 0.1. And Okay, so we'll take this and just drag it upwards because this controls the simulation, and here we have this parameter of time of flight, and here we've plotted the function, and then hopefully we can see, yeah, it's at the end here. You see this point that was added. And now if I click play here, for some reason it's stuck here. Maybe I need to give it a more delicate step here. 0.01. Let's see. Okay, and let's try and see. Yeah, it's moving slowly. You see this moving over here. And so we've already created some simulation. And actually, we can see that if I increase the speed, then it's moving faster. See? If I were to increase the speed again, then you see that this is going to be, yeah, it should be moving in this direction, but we can think of it being thrown in the opposite direction. It just shows that the laws here, the laws of physics are reversible in time. So one time when it moves from here to here, it's thrown from here and backwards as though it was thrown from here with the same reflected angle here. So we see this visualization, and we can maybe make this trajectory as being invisible. So let's change the color here. So let's go to here and let's change the color here to this black and dashed. This is imaginary invisible trajectory, and done. And so we see how this point moves, and we can move it ourselves. And yeah, we see the effects of gravity and of the angle and of various things. But yeah, and of the angle, of the gravity, and of the initial velocity, how it affects this trajectory. But actually, for a given velocity here, let's just zoom out a little bit. For a given velocity, say, let's zoom out here. Let's take a bigger velocity here. And again, zoom out. Okay, let's see a family of curves. So now I want to draw this peak, the peak height. And this is done very easily because from symmetry consideration, it's at half of time of flight here, right? And so I can write f of t and call it just, call this dy, maybe. Yeah, that's the maximum value of y. We want to call this way. Let's call it m, right? M would be this, and this is this point. And we can call this, we can even add label, and this is max height for this trajectory, right? So the maximal height is going to be at this point, and we see it exactly here. And now suppose that we want, so there is our points, so we want to see other trajectories. So let's plot a few more trajectories. So for that, I'm going to take the function. Yeah, let's derive the. I haven't proved that this is a parabola. So let's derive and see that these equations, those parametric equations. Let's see that this is indeed a parabola here. So let's go to here and derive those equations. So the equations that we have is that x of t is v0 cosine of phi times t, and y of t is v0 sine of phi times t minus half gt squared. And so we have the dependence of x on time and of y on time, but if we want to plot it, we don't have the dependence of y on x, and that's what we're going to derive. Suppose that this is y, and this is y, and this is the x. So how does y for each point x here? How does y is dependent on x? And so for that, what we can do here is we can just find t, express t as x. So t is actually x divided by v0 cosine of phi. And then we can plug it into here instead of t. So what we get is y, or y is a function of x, is going. So this v0 is going to be reduced. So it's going to be tangents of phi times x. And notice how actually this makes sense, because if this angle phi, then the slope of this line, of this tangent line, actually the direction of the velocity, is tangent here, and the slope is actually the tangent of this angle phi. So it makes a lot of sense. So it's tangent phi and minus 1/2. So g, and here we need to take, this is going to be x squared divided by v0 squared cosine squared of phi, right? So this is the equation. We see that this is the parabola that I was talking about. So for each x and y here, so knowing some points on the trajectory, measuring them, we can then derive 3 points would enough to derive the entire curve here, or even, yeah. So we actually need to know this angle phi, and that's it. So we have this, we've proved that this is a parabola, and the reason that this is a parabola is because of the nature of the motion with constant acceleration and close to the surface of the Earth, of course, with neglecting the drag. This is a motion with constant acceleration. So now let's draw this parabola in Desmos and see how it looks and see a visualization of this. So now if you go to here, right, so let's draw this parabola. Let's give it an equation. So let's say somewhere over here where we have our functions, we'll click enter here. And so we will write this y equals the tangents. We need to write ton of phi, and here times x. And so we see this tangent line with the required slope minus 1/2 times here, of course, times g times and here we're going to have x squared divided by x squared, and here divided by v0 squared times the cosine of phi and all of it squared. Okay, and so we see that it coincides with this curve, and we have this excess plot that we may not want to see for aesthetic reasons. And so what I can do here, I can do those brackets, and I can say y greater than 0. And so we see that this trajectory of this curve coincides. So if I now press play, then this is what I get. But suppose that I want to see this for various angles here, and let us plot a family of those. So let me just define a list of values. S would be this squared brackets means this is a list from 0, and then basically I'll define a step 0.1 and say here 3 dots up to p. So from 0 to pi, this is a range of angles, and here I will write, then I will go to here, and I will say, you can go to here and say here duplicate. So I have the same formula. This is, I'm done here. And now instead of phi, let's substitute s, right? And we get a range of trajectories, s. Okay, and so we see that, as you've seen in the promo, we see those possible trajectories that we can see here. And then when we, let's take this, and let's make this curve, the current curve, let's make it black, or let's change its color to something that is more, let's say this is purple, right? Let's make it purple, okay, or orange, I don't know what's, instead of red, let's maybe, yeah, let's make it black. Okay, done. And so now that we play with the angle slider. Oh, I set phi to be this, but I want a slider for phi. Okay, I need a slider for phi. Just a second. Just something got stuck here. Yeah, here I needed to add the slider. Fine. Yeah. Okay. Good. Okay. So now that I have the slider for this angle phi, if I adjust it, so phi would be from 0 to pi, from with step of 0.1. Then when I take the slider here, right? So we see that this trajectory. First of all, we see this peak over here. Let's take c to be 0, the origin. Okay, and then we see that when we adjust the angle, then it's coincides with one of them. Those are the possible trajectories. So we see this beautiful geometry here. And what would be interesting is to trace where is this peak located, right? The parametric equation for the peak. And so we can do that, because what we have here is what we need to take here. Basically, we see that it's in the middle time of flight. So if we will take here and plot, let's take it like that. So let's take that. Control C. Let's copy that, and let's go into here, right? And now let's plot the curve where we take t to be this maximal range, but half of it, half time of flight, we're at the peak. So this is Control C. Let's copy that, and instead of that, let's just plug this in, times that, and here it's going to be times that, and that's going to be times that. We'll make the computation, and we want to plot this. So now phi, we want to make it for all, not for the specific angle phi, but for all angles phi. T and T and T and T. Right, so we want to see how it looks. It's mid-time flight for all possible T's. So T is going to be from 0 to pi. And we want to plot this and see what we get. Yeah, so we get this ellipse that you've seen. We can adjust its color. And then we see that as we move the slider for phi, we see that this middle point, this peak, is on this ellipse. We'll actually prove that the equation for this is an ellipse shortly. But then we see those possible trajectories, their geometry. And we see this ellipse that this vertex traces here. And so we also see that as we add more here to S, so if we can go here and say make it 0.01 for the extreme, and we see that all these possible trajectories form, there's some envelope encompassing them all, and we'll find the equation for this envelope, which also turns out to be a parabola, right? So let's go and do some more analysis here. So of course, when we get back here, we have seen that this is a parabola, and now we have computed the maximal range here, and so this is the x, and we've seen that, let's call dx the maximal range. And so the maximal range, we see that this is for phi equals pi quarter, so let's call this v0 divided by g, v0 squared divided by g, and maybe add it to Desmos, okay? So if we go to Desmos here again, and we add it, so let's add here some constant. And it's really a lot, resembling a lot the design of software, in that you can really build it structurally. So let's go, say here, and maybe let's make it a bit sparser. This is 0, 0, 5, and let's go here and add the constant. So call this dx, the maximal range in x, and this is going to be v0 squared divided by g, right? And so let's call this, okay, so we have that, and let's have dy. And so the maximal range in y, dy, let's call this, it's going to be half, this is just half of dx. Let's just define those constants. And so if we were actually to plot this here, let's plot this y equals dy. Yeah, we see this line, right? Let's make it dashed orange, okay? So let's click here, let's go to settings, and let's just make it orange dash like this, as this delimiter. Okay, so we see that this is this bond of this region. This is of course 0. This is the center. This is the y equals half. And of course, if we here we'll see that we know that the vertex here is also mid-range. So when we trace this curve over here, right, we see that this is mid-range. So this is going to be half of the maximal range in x. So let's call this. Let's plot also here. X equals, like that, x equals dx. This is, and make it again dx divided, yeah, this is this maximal range. Okay, we can leave it like that, and let's plot x equals minus dx. So we see that this is the, let's make it black as well. Okay. And this is this line over here, and let's plot something else here, dx divided by 2, so it's going to be x equals that. Let's make it here, so we'll make it orange, and we'll make it dashed, and plot here x equals minus dx divided by 2, and make it again orange. Okay, orange like that. And so we see that those are the edge points of this ellipse. So by now it's a bit cumbersome, but remember that we can always, turn off every part that we want. So we can now see the geometry and the invariants of this problem, the maximal range, and how the vertex is constrained to move along this ellipse that we see here. And so finally, we'd like to derive the equation for the envelope.